This is lesson 17 in our Calculus 3 series, Directional Derivatives and the Gradient Vector. Let's start this lesson by recalling some definitions from lesson 14. For the x partial derivative, we have limit as h goes to 0, f of x naught plus h, comma y naught minus f of x naught y naught over h. Notice that y naught is fixed here, and we're looking at the change in z values with respect to a change in x values. So if we take a look at that visually, the y naught is fixed. We're restricted to this line, y equals y naught, and we're looking at the change in z as h goes to 0, as these 2 points get closer together. This is x naught, y naught, this is x naught plus h, y naught. So we're taking this difference quotient as h goes to 0. Similarly, for the y partial derivative, we're fixing x naught, so we're along this purple line here. Here's x naught, comma, y naught plus h. So we're looking at the rate of change as h goes to 0 here. Now let's take a look at the directional derivative of f at x naught, y naught in the direction of unit vector u. The definition looks like this. Directional derivative in the direction u of f at x naught, y naught is equal to limit as h goes to 0. Notice here we have the h in with the x and the y terms. We have x naught plus hu1, where u1 is the x component here, and y naught plus hu2, where u2 is the y component here, minus f of x naught, y naught over h. So let's see graphically how this makes sense as a derivative in the direction of this unit vector. Here's our unit vector placed at the origin. U is equal to u1, u2. And here's our point x naught, y naught. Now notice we can talk about the line in direction u through x naught, y naught as x equals x naught plus hu1, y equals y naught plus hu2. This is very similar to the parametric equations for the line in three-dimensional space, only now we're in two-dimensional space. We've got our direction vector u1, u2, our parameter h, and this is a parametrization of the line through x naught, y naught in direction of u. So that means that any point on this line is going to have, for some h value, is going to look like this, x naught plus hu1, y naught plus hu2. So when we're looking at our function value at this point as compared to our function value at x naught, y naught, we're talking about a rate of change that we're computing here, right, with a difference quotient. We're talking about a rate of change, but it's in the direction of vector u. Now notice with this definition, if our unit vector u is equal to I, the standard basis vector, 1, 0 in the two-dimensional plane, then our directional derivative reduces just to the x partial derivative formula. Similarly, if our unit vector u is equal to j, our directional derivative reduces to the y partial derivative at that point. Now let's take a look at what all this means in terms of surfaces. Here's our domain, and here's unit vector u. Here's our point x naught, y naught, at which we're going to take the directional derivative. And here is x naught plus u1h, y naught plus u2h. Here's the point x naught, y naught, f of x naught, y naught on the surface. And when we're talking about the directional derivative, we're talking about the plane through x naught, y naught in direction of u, right? So it's this plane here, intersecting that plane with the surface and taking the slope along that curve. That slope is a directional derivative of f in direction u at x naught, y naught. Now compare that to the x partial derivative and the y partial derivative. It's the same point here, but the x partial derivative is what we get when we fix a y value. And so we're looking at the curve of intersection between the plane y equals y naught and the surface z equals f of xy. at the point x naught, y naught, and we look at that slope. That's the x partial derivative at that point. Similarly, the y partial derivative is what we get when we intersect the plane x equals x naught and the surface, and so we're looking at that curve of intersection and we're getting the slope of that curve. That's our y partial derivative. So here we're at the point x naught, y naught, but this plane is slicing in the direction of unit vector u. And that gives us the directional derivative in direction u of f at x naught, y naught. So now we've seen the limit definition of the directional derivative, but how do we compute it? Well, we have this theorem: if f is a differentiable function of x and y, then f has a directional derivative in direction of any unit vector u, which is u1, u2, and we compute it this way. Our directional derivative is given by the x partial multiplied by u1 plus the y partial multiplied by u2. So take the component notation of unit vector u, and you're going to kind of take a weighted sum of the x and y partial derivatives with these components. That's your directional derivative. So let's take a look at an example. For the surface f of xy is equal to 4 minus x squared minus y squared, let's find the directional derivative at the point 1/2, 1/2 in direction of u, which is 1 over radical 10, 3 over radical 10. Now notice it's important for u to be a unit vector in order for this computation to be valid. So we compute our x partial and our y partial derivatives here. That's negative 2x for the x partial, negative 2y for the y partial. We're multiplying by our components u1 and u2. And so in terms of x and y, our directional derivative looks like this, but at a particular point, at the point 1/2, 1/2, we plug in x equal 1/2, y equal 1/2, and we get negative 4 over radical 10, or if you want to rationalize and simplify, negative 2 radical 10 over 5. And let's take a look at that graphically. This is the surface f of xy equals 4 minus x squared minus y squared. This is our point 1/2, 1/2. This is in the direction of unit vector u. And so what we found is that the slope at this point in the direction of this curve of intersection here, that slope is equal to negative 2 radical 10 over 5. That's our directional derivative at this point in direction of unit vector u. Let's take a look at another definition. If f is a function of x and y, the gradient of f is the vector function del f of xy is equal to, notice the x component of this vector is the x partial derivative of the function. The y component of the vector, the y partial derivative of the function. We could also write this in standard basis notation this way. Now then notice our directional derivative, which we said is the x partial times u1 plus the y partial times u2, that's going to be this gradient vector dotted with vector u. Now let's find the directional derivative of f of x equals 3x plus 2y squared minus 6 cosh of xy at 2, 1, heading toward the point 1, 2. Well, notice they give us the function, they give us the point at which we're taking the directional derivative, but they didn't give us the unit vector. Instead, they said the direction from 2, 1 to the point 1, 2. So we have to come up with the unit vector ourselves. So the first thing we're going to do is find a vector in the proper direction, then we're going to scale it to be a unit vector. So finding the vector from 2, 1 to 1, 2 looks like this. We've got negative 1, 1. And we recognize that its length is equal to radical 2. So in order to scale this to be a unit vector, we're going to divide each component by radical 2. Negative 1 over radical 2, comma 1 over radical 2. That's the unit vector that we need for our directional derivative. Now that we have the component notation of the unit vector, we can go ahead and find our x partial and our y partial derivatives at the point 2, 1 and complete the computation. So here's our function. Let's take a look at our x and y partial derivatives. Our x partial derivative is going to look like 3 plus 2y squared minus 6 times, now derivative of cosh is sinh, so sinh of xy multiplied by the x derivative of what's inside. and that's going to be y. So we have 3 plus 2y squared minus 6y sinh of xy. And so at the point 2, 1, we get 5 minus 6 sinh of 2. The y partial derivative is going to be 4xy minus 6x sinh of xy. And plugging in the point 2, 1, we get 8 minus 12 sinh of 2. So our directional derivative looks like this. And doing a little simplification, we get 1 over radical 2 times 3 minus 6 sinh of 2. Now let's talk some more about the gradient and the directional derivative. We're talking about derivatives now in all different directions. At first, we were restricted to just the x and y directions with the x partial derivative and the y partial derivative, but now we're talking about derivatives in all directions. And so we might be interested in knowing which direction is going to give us the maximum increase in z, the steepest slope. Where can we find the steepest slope at any point? Well, let's take a look at our directional derivative. We said that could be written as the gradient of f dotted with unit vector u. Well, we know a dot b is length of a, length of b, cosine theta, where theta is the angle between the two vectors. So gradient of f dotted with u is equal to the length of the gradient of f times the length of unit vector u times cosine theta, where theta is the angle between the gradient and the unit vector. Since this is a unit vector, we know its length is 1. So our formula simplifies a bit. And so now we have that the directional derivative of f in direction u can be given by the length of the gradient multiplied by cosine of the angle between the gradient and the direction vector u. Now if we're trying to find where this directional derivative is maximized, where we're going to have that maximum increase, that steepest slope, we want to look at the right-hand side and say, for which angle are we going to have this maximized? Well, we know that cosine theta is maximized when theta is equal to 0 and cosine theta is equal to 1. Well, theta equals 0 means that u is in the same direction as the gradient. So the directional derivative in the direction of the gradient is going to give us the maximum derivative. In other words, the maximum rate of change, the steepest slope. And notice that the maximum value of that derivative is then going to be the length of the gradient vector, because this is going to be 1 when theta is equal to 0. So that tells us the steepest slope we're going to get is in the direction of the gradient, and the steepest slope is the length of the gradient vector. Also notice then, if we're using the same formula for the directional derivative, now looking at the length of the gradient vector multiplied by cosine of theta, we know that this is going to be equal to 0 when cosine theta is equal to 0, and that happens at theta equals pi over 2. In other words, when there's a right angle between the gradient vector and the unit vector. So the directional derivative is 0, meaning there's no change in z when we're going perpendicular to the gradient vector. So when u is orthogonal to the gradient vector, when the angle is pi over 2 between them, there's no change in f. That means that u is tangent to level curves of f, which means that the gradient vector is orthogonal to level curves of f. So summing up, we have these three statements. The gradient of f at any point points in the direction of maximum increase of f at that point. The length of the gradient vector is that maximum slope. And the gradient vector is orthogonal to level curves of f at any point. Now let's take a look at the idea of skiing down this mountain. Taking a look at the view from the top, we can see the contour map, and we can see that if we're starting around here, our steepest path would be right down. Now we just learned that the gradient vector at any point is going to be orthogonal to level curves. What that says is that for a flat contour map, think about this contour map in the two-dimensional plane, the gradient vector is going to be orthogonal to each of the level curves. So from each of the level curves that we see, that gives us the approximate path that we have here. But think about when you're skiing, you might not want to take that steepest path down, right? So instead, you might want to take a less steep path by going side to side. Notice that if we're not going perpendicular to the contour curves, we're getting a less steep path. Let's take a look at a couple more surfaces that we're familiar with. Z equals x squared plus y squared, the elliptic paraboloid. And let's take a look for this surface. Let's take a look at the gradient vector field and the level curves. So we've seen the contour map before, so this we are familiar with. But let's take a look at the gradient vector field. We're looking at our domain in the xy plane, and the gradient vector field gives, at any point in the domain, the gradient vector at that point. But just keep in mind that this software I'm using here isn't scaling the vectors to the proper lengths for the gradient. It's just showing the proper direction. And notice if we superimpose these two images, these vectors would be orthogonal to the contour curves. And remember, the gradient vector points in the direction of maximum increase. So notice that we have our minimum here at x equals 0, y equals 0. That's what's going on here. And so these vectors are pointing in the direction of maximum increase along this surface. Now let's take a look at our hyperbolic paraboloid, z equals x squared minus y squared. And let's take a look at its gradient vector field and level curves. Remember that the gradient vectors point in direction of maximum increase. So we can see that along the y-axis, we're getting a maximum in that direction. Along the y-axis, we're getting a maximum in that direction, right? Those vectors are pointing inward towards the origin. But in the x direction, we have a minimum. Those vectors are pointing outward, away from the origin. In the x direction, we have a minimum, and those vectors are pointing outward, away from the origin. And again, if we superimpose the gradient vector field with the contour map, we would see that the gradient vectors are orthogonal to the level curves. So we said our gradient vector is orthogonal to level curves. Those are equations of the form f of xy is equal to a constant, and therefore the gradient vector is also orthogonal to tangent lines to level curves. Now we're going to take this into 3 dimensions and talk about level surfaces and tangent planes. So first, let's recall what level surfaces are. From lesson 11, we had f of xyz is equal to x squared plus y squared plus z squared. Now when we take a function of 3 variables and set it equal to a constant, we're getting a series of surfaces. In this case, we've got the spheres of different radii, so that gives us a collection of spheres of any radius, and that's the collection of level surfaces for this function of 3 variables. Now, for a function of 3 variables, w is equal to f of xyz, we have the gradient vector defined to be the x partial, y partial, and z partial in component notation. This gradient vector we're going to see is normal to level surfaces. Those are equations of the form f of xyz is equal to a constant, and therefore the gradient vector is also normal to tangent planes to level surfaces. So consider a level surface f of xyz is equal to k, and any unit vector u in the tangent plane to that level surface. So consider one of the spheres that we have above, if you want to get a visual, and consider a tangent plane to the sphere. U is going to be any vector in that tangent plane. Since u is in the tangent plane, we know the directional derivative of f in the direction of u has to be 0 because it's a level surface. We know there's no change in f for directions that are tangent to this surface. So that says 0 is equal to our directional derivative of f at x naught, y naught, z naught, and that can be written as the gradient vector at that point dot product with unit vector u. That's the vector in our tangent plane. And so that tells us that the gradient vector and u are orthogonal. So that tells us our gradient vector is normal to the tangent plane and therefore normal to the surface, to the level surface. So for the example that we had above with the spheres, f of x, y, z is equal to x squared plus y squared plus z squared. For the level surface x squared plus y squared plus z squared equals 9, consider the tangent plane at 1, 2, 2. We now have that the gradient of f at 1, 2, 2 is normal to the tangent plane. So this is an easy way to find a normal vector to the tangent plane to the surface at this point. So here our gradient of f is 2x, 2y, 2z. And so at the point 1, 2, 2 we get 2, 4, 4. And so that is a vector that is normal to the tangent plane at 1, 2, 2. So that's our normal vector, ABC. We have the point 1, 2, 2 goes in for x naught, y naught, z naught, and that's an equation for our tangent plane. Now we can use this method to answer questions that we had from back in lesson 15, find an equation of the tangent plane to a surface at a particular point. And let's take a look at how we can do that. If we're given, find an equation of the tangent plane to the surface given by x squared plus 4y squared plus 17 equals z squared at negative 2, 1, 5, well, we could create a function of 3 variables, capital F, and consider this surface to be a level surface of this function. So I'm going to create my capital F to be x squared plus 4y squared minus z squared plus 17. So I'm bringing the z squared over, and then I'm saying that our surface is the level surface, f of x, y, z is equal to 0. And so we're looking for a tangent plane to this level surface at this point. Well, how can we do that? We can find our gradient vector, 2x, 8y, minus 2z. At the point negative 2, 1, 5, we get negative 4, 8, negative 10. And so here's an equation for our tangent plane at the point negative 2, 1, 5. Now we could also use the methods that we learned back in lesson 15. Back in lesson 15 we found that this equation would be an equation for the tangent plane to z equals f of xy at the point x naught, y naught. But notice we're not given z written explicitly, we're given x squared plus 4y squared plus 17 is equal to z squared. So we would need to use implicit differentiation here to get these partial derivatives. And using implicit differentiation gives us partial z with respect to x is x over z, partial z with respect to y is 4y over z. And we can plug partial z with respect to x at negative 2, 1, 5 here, and partial z with respect to y at negative 2, 1, 5 here. So that's a negative 2/5 and a 4/5 for our partial derivatives at that point. And so the tangent plane can be written like this. Now notice, if we just multiply this equation by 10 on both sides, we get the same equation that we had above, which was negative 4, x plus 2, plus 8, y minus 1, minus 10, z minus 5 equals 0. Right, so it's a different form of the same equation. They both represent the tangent plane to the surface at that point. But it seems like the new method is a bit quicker. So it's kind of a smarter way to go to take our surface, recognize it as a level surface to a function of 3 variables, compute the gradient at the point, and go straight to an equation of the tangent plane. And we'll conclude our lesson on the directional derivative and the gradient vector here.